Hi everyone. To warm up today's stream 2, we have Sohaila Diab, data scientist at Bizanex. She will introduce us to the power retrieval augmented generation RAG in creating more accurate, relevant, and trustworthy AI systems covering speech recognition and more. And thank you everyone for attending. Okay, you can start.
All right, thank you for the introduction, chat. Hi everyone. I'm Sohaila. I'm a data scientist at Next, and I mainly work with NLP, work to solve complex business problems using AI and analyzing their data to extract insights for them. So today I'll be talking about RAG and how to talk to your data. So let's get started. The agenda for today, first we'll be going through the LLM foundations. What are LLMs? The limitations of LLMs, and then we're going to dive into the introduction of RAG, and then go into deeper details about RAG, and then we're going to have a code walkthrough and build an actual RAG model. So you'll be able to build a RAG model. And then we're going to see the challenges we face when using RAG and what are potential solutions for these challenges. And then that's all. And it was going to be time for the Q&A. So first of all, what are LLMs? LLMs, they are advanced AI models trained on a huge amount of text data. And basically, the LLM stands for large language models, and the large comes from the model size, because the model size is huge and it is trained on so many data, so many parameters, billions even. So this is where large came from. And language is because it specializes in text, it specializes in natural language, understanding it and generating it. And model because it is basically a deep learning based AI system, and it learns just like any deep learning model, and it learns language patterns, and it learns the patterns coming from the data to be able to generate responses. So let's continue looking at what makes LLMs so powerful. First, they're built on the transformer architecture, which is the foundation that enables them to understand and generate language efficiently at scale. And actually, the breakthrough behind the transformers, this was a huge breakthrough behind the language models, and it was like the starting point of LLMs. And this transformer architecture was introduced by Google in 2017 in a paper called Attention is All You Need. And this basically replaced other older models that were used, such as the RNNs, LSTMs, and now the transformer architecture enables the LLMs to scale effectively, understand the context. And secondly, the second thing that makes LLMs so powerful is that they're trained on massive amounts of data, huge amounts of data. Their performance is great because they're trained on a lot of data, and we're talking trillions of words, covering things like from Wikipedia, from books to code and web pages. So it's trained on data from the internet and so many data. And because of this training, they can perform a wide range of language-based tasks, such as answering questions, summarizing documents, translating text, generating code, and much more. And often it is with human-like fluency. And you might have noticed that they keep getting better and better. Like if you have tried GPT-3 and then tried GPT-4, you're going to notice a huge difference. And this is also because GPT-4 is trained on much more data than GPT-3. and it is starting to answer more like a human. And these capabilities basically power many of the tools we use today, like ChatGPT, which we all know, Claude, Bart, and Copilot. So here you'll see a chart showing basically how training datasets have grown over the years, not just in terms of model size, but also in the volume of text they're exposed to. For example, Meta's Llama 3, it is exposed to 70 billion parameters. So that means it is trained on huge amounts of data, about 10 trillion words. So this is an incredibly large data set. And this growth in data and compute is what keeps pushing the boundaries of what LLMs can do. And I just want to show you. I want you to imagine how much data these models are trained on. Like for example, we can see here GPT-4. It's supposedly, it's not official, but it's supposedly trained on over 1 trillion words, and this is 100 times more than the words that an average human has read or heard in their lifetime. Like an average human has read or heard around 1 billion words. However, GPT is trained on around 1 trillion words. So it is exposed to over 1 trillion words. So as you can see, they are exposed to so much more data than we are exposed to. But the thing here, here's the catch. LLMs don't know what they don't know, meaning that they can hallucinate. They can make up facts with full confidence. Like, for example, you would ask it a question, for example, who won the World Cup in a certain year, and if it didn't come across that answer, if it didn't come across that data before, it's gonna hallucinate. It's gonna be confident in the answer, but it's gonna be an incorrect answer. So this is an issue. The hallucinations here is an issue. And if, for example, if you ask it something specific to a course that you're taking, that the LLM was not pre-trained on, it's also going to give you a confident, or might give you a confident but false answer. It doesn't tell you, I don't know. They also rely on training data they've been exposed to, which can be outdated or lacking in certain domains. So there's like a stopping point on which LLM, on the LLMs, on the data that LLMs are trained on. Like, before they publish it, they train the LLMs, or they pre-train the LLMs on a certain amount of data, and there's a cutoff year. So for example, if the LLM is trained until January of 2025, if you ask it about an event that happened in February 2025, it's not going to be able to answer you, and it will probably give you a confident but incorrect answer. So so the issue here is that also if the data they were trained on didn't include, like I mentioned, specific domain expertise or events, the answer they will generate will reflect that limitation. And yes, they've been trained on huge amounts of data, but this data is general. It's not really domain specific. It's like, when you're browsing internet, you see everything. It's not very domain specific. It's not targeted towards something certain. And because LLMs don't have awareness of their own gaps, they will always try to answer, even if they don't know the actual correct information. And this is why they can seem overly confident in providing the wrong answers. Let's have a quick poll. I will create a poll. I'm interested to know have you ever seen an LLM make something up? Let me create one. So I posted a poll. You can see the poll on the right-hand side of the screen, and we can take a look at it after the session. So this is the issue. This is where the lack of reliability, and it is where the trust breaks down. And in high-stake areas like health, law, education, or finance, accuracy really, really matters. It is very important, and this is where these problems become very critical. And to give you an example, a well-known example of LLMs causing issue happened in a New York federal court. And one of the lawyers actually was caught citing non-existent cases. And when they were after they investigated, it turned out that he was using ChatGPT to conduct legal research, and the bot referenced fake cases to the attorney, which is a huge, huge problem. And this attorney faced serious consequences, like a $5,000 fine, and the case was completely dismissed. And this shows what LLMs that while LLMs are powerful tools, they're limited in certain areas, especially when it comes to ensuring the accuracy and reliability of information, and also having the up-to-date information. So new methods like RAG actually are being introduced to enhance LLMs to connecting them with trusted sources and real-time data. So let's dive into how RAG works and why is it so important. So what is RAG? RAG is Retrieval-Augmented Generation. It combines the power of LLMs with external data sources. So instead of only relying on the model's training data, the data that the model has been basically pre-trained on, it can access more accurate information. So it can access more accurate and up-to-date information. And their first step in the process is retrieval. So this is where the R comes from. And this is basically means that the system pulls out relevant information from trusted sources that you provide, such as databases, like a certain database that you want the LLM to get its answers from. And this allows the LLM to gather information beyond its initial training. So now that instead of only using data that it's been trained on, it has also another source of data, a trusted source of data it can look at. The second step is augmented. And this part, it adds the retrieved information to the model's knowledge. So it gives it access to real-time data or domain-specific knowledge. This enhances the LLM's understanding of the topic. And finally, the D for generation. This model, the model then uses enhanced information to generate response that's not only more accurate, but also better informed. So now instead of looking at the old data and like we have retrieved the relevant data, we have added it to the AI's knowledge, and now it's going to generate the answer based on the new data that it retrieved. So this data is more accurate, so that means its answer is going to be better informed, its answer is going to be more accurate, and this leads to the AI being more reliable, and especially when answering complex or specialized questions that might not be, general knowledge or something that it's been generally trained on. So you might be wondering, why would we bother using RAG? And it boils down to some advantages. And the first thing is it has sharper accuracy, because the model is pulling relevant data. It is pulling the accurate data that you've provided. That means that data is correct. It is less likely to hallucinate or be outdated. So it is less likely to give you an answer that is outdated. Like if you ask it a question, it's gonna give you an answer based on data that pulled out from the database that you provided or whatever data source that provided it. So it's not gonna make up an answer. The next is on-topic relevance. So the RAG ensures that the model stays focused on your specific query, not drifting off topic with unrelated general knowledge. Because like we mentioned before, it is the LLMs are pre-trained on general knowledge. So when you give it precise knowledge that you want it to look at, is going to be more on topic. And this is especially important in domains like legal, healthcare, and finance, where accuracy and relevance are very important and non-negotiable. And then the real-time retrieval. The knowledge is fresh and up-to-date, but this is given that you update your data sources or update your database. So if you give it a database that is regularly updated, it would have access to fresh and up-to-date knowledge. So next, let's break down how RAG operates and how the workflow basically operates in practice. So the first thing is the user query. So you send it a message. The process begins when the user submits a query. This could be a question or request for information. And then this user query passes by something called an embedding model. And these blocks will actually dive deeper into it in the next slide. But this embedding model basically, it passes through, it transforms the user query into a vector representation that can be used in the next step. So it transforms basically the user query in a format that can be used in the next step. So it breaks down the user's query, transform it into certain vectors. This is what the embedding model does. And then we get something called a vectorized message, basically. And this message, well, before it gets into the vector database, we have something called the vector database, and this is basically the database that the RAG would take its information from. Then this vectorized message is sent to the database, and this database has data in it. And this data can come from things like PDF, PowerPoint, YouTube video, and basically you pass in the content also to another embedding model, and the content that you give it will be transformed into a sequence of vectors, which will be stored in the vector database to be used for looking up information. So imagine this vector database kind of like a library. When you go to a library, you can see there are sections where you can look at for specific genres. So this is kind of the vector database is kind of like a library. And then this database, the goal was to retrieve the vector database. It retrieves the n most similar passages. So we have now the vectorized message and we have the vector database. We want to see this vectorized message. How relevant is it? Like, what are the relevant passages inside the database? So, for example, I'm asking it a specific question about how to make pizza, for example. For this, imagine data is for a pizza restaurant. So I'm asking it how to make pizza. So it takes a keyword or the vectorized keyword and it searches in the vector database using something called similarity scoring, and it finds the most similar passages. So it's probably going to find passages like the instructions for making pizza is so and so and so. So it then extracts these passages, and then we go into the augmentation. So now that it has the similar passages, it passes it into the prompt. And this is the prompt that we already have for the LLM. And aside the prompt, we pass with it also the passages that we extracted. And then we get to the generation part where it goes to the LLM and it outputs a response back to the user. So let's dive deeper into the each step. So we have the embedding model. The first key component is of the RAG is the embedding model. And an embedding model is responsible for transforming text like your user query or the content in the database. So, because we have here two embedding models, the user query and the content in the database. It is used for transforming it into vectors. And these are numeric representations that capture the semantic meaning of the words. So, because the computers, they don't understand language; they understand numbers. So the semantic captures the semantic meanings of words. So it transforms basically these words into a vector of numbers. In other words, similar concepts will be closer together in a vector space. And these vectors helps the system understand the underlying meaning of the text, even if the exact words are not the same. For example, doctor and physician would be close to each other in a vector space because they have similar meanings. And popular embedding models include SentenceBird, OpenAI's embedding API, and there are also many other embedding models. And these models make it easier for the system to search for and retrieve information quickly by turning everything into a vectorized format. So this is pretty much how the embedding model is. So you pass in text, for example. So this object is text. You pass it into the embedding model, and it transforms it into a sequence of vectors. So, for example, here is doctor and here is physician. And the doctor, physician, and let's say cat. So that means that these two, the first two, would be similar or would be closer to the vector space, closer together in the vector space than the cat. And we'll see together how a vector space would kind of look like. So next we have a vector database, and this is basically where it stores and indexes all the vectorized data. So this is where it stores this information here. The content that has been transformed into numeric vectors by the embedding model. When a user submits a query, the database uses similarity search, such as cosine similarity, and this is to compare the vector query to the other stored vectors in the database. And this comparison allows the system to retrieve the most relevant and the most the content that matches the most to the user query. And because of the vector format, the search is faster and more accurate than the traditional keyword-based searches. Because it has numbers, it just does some calculations to get some similarity search calculations, like cosine similarity, to quickly find the similar vectors. And some popular vector database include Pinecone, Thies, and Weaviate, and which are designed to efficiently store and search large-scale vector data. So this is to visualize it, kind of. This is what an imagined or imaginized version of a vector database would be like. Like you can see here, the bananas, green apples, and pears, they're pretty close to each other. And boats and ships, they're close to each other, but far from here. And then we have football here, which is far from the rest. And this is kind of what a vector space would look like visualized. Next, as we move on to the retrieval process, it is crucial to understand its role in the RAG pipeline. So in this component, the system fetches relevant documents from the database, and this process is driven by similarity search. So this is where the user's query is compared against the vectors and representations of documents. The vectors against these user queries are compared to the vector database, the documents in the vector database. And we do the similarity search, like I mentioned before, maybe with cosine similarity to get the similar vectors. And this is inside a vector store, like we do the search inside the vector store, like we mentioned here, the vector database, like Pinecone, to get the to enable efficient similarity searches by representing documents as high-dimensional vectors. So think of it kind of like needles in a haystack. So instead of keywords, we are using very high dimensional vectors. So these vectors are huge. They're not as small as this. They're huge vectors, and basically these vectors, we use them to represent the documents that we have. So they're representing the data that we want to use in the RAG, and this ensures more accurate results because it represents the meaning of the word. So once we retrieve the relevant documents, the next step is augmentation. This step enriches the input to the language model. Essentially, we provide the model with additional context by appending the context to the retrieved document, to its prompt. So we have a prompt, and then we get the retrieved context, which is like the context coming from the vector database that are similar to what we're searching for. And then it gets appended to the prompt, and this basically ensures that the model's response is based on the most relevant and up-to-date information available, improving the overall quality and accuracy of the answers. And this augmentation process allows for language models to answer domain-specific queries more efficiently. So it looks at data beyond that's pre-trained, beyond the data that it's pre-trained on. And lastly, the generation process. And the model, basically, the generation process is where the LLM comes in. So it's basically the model uses the context we've provided, including the original query and the augmented data, and as well as the prompt, if we pass in the prompt, and to generate a coherent response. And this is the most visible part of the process, where the model takes the transformed query and context to output a final answer, which is basically what is outputted to the user. However, the quality of this response depends heavily on how we design the prompt for the LLM. So a good prompt ensures that the model focuses only on relevant aspects of the input. Like, for example, you tell it, don't answer outside the data, that the context that has been given, so that it doesn't go out of the context. And this needs some prompt engineering, and because poor prompts eventually could lead to wrong or irrelevant answers. So you might be asking, what is the difference between RAG and fine-tuning? Like, why are we not fine-tuning the model instead of using RAG? And let's first break it down on when to use RAG and when to use fine-tuning, and why would we, when would one make sense over the other? But first, fine-tuning is basically you take this pre-trained model and you fine-tune it on new data. So you train it again, you retrain it on, you fine-tune it, you give it new data to look at, to train on. And this is basically fine-tuning. And this data is basically kind of like the data that's that you want the model to have more information about. So basically like specialized data or data about something specific. So when to use this and when to use that. RAG is ideal when you want to have something very quick that is up to date and has specific domain knowledge into your AI system without retraining the whole model. You won't need to retrain anything. It's mostly just plug and play. And it is modular. So you have a vector database and relevant documents. You put the relevant documents in the vector database, and there you have the vector database that it looks at. And it's much faster to implement. It doesn't require massive amounts of data. Like you're not training it, so it doesn't require huge amounts of data. And so that means that it is significantly more cost effective, and both in terms of the compute and time. So training models, especially large language models, use a lot of resources and a lot of time. So you will save up on resources and time. Also, updating the knowledge database is simple. So all you have to do is update the vector database that you have. So it's easy to update the content that you want the LLM to have information about. On the other hand, fine-tuning is more about shaping the behavior or the tone of the model itself, not just its knowledge. So it's great when you need the model to behave in a very specific way across all tasks, to have very specific information, but it's very, very resource intensive. You'll need a large curated data set with lots of RAM and lots of GPU. So, like as you've seen before in the previous slides, the LLMs are trained on huge amounts of data. So the fine tuning would need less data, obviously, than the pre-training, but it still needs a lot of more data than the RAG. And plus, once fine-tuned, updating it with new knowledge is not trivial. It's not very easy to do. So it usually means another round of fine-tuning. So if your priority is more of knowledge freshness, having the LLM have fresh knowledge, have the LLM would be fast, and you want to save costs, so you would go with RAG. If your goal is to teach the model how to think and respond in a very specialized way across context, and you have enough resources and you have enough money to do so, then the fine-tuning would be the way. So before we jump into the coding aspect, let's take a moment to understand LangChain. And this is the framework that we'll be using in the code. And so LangChain is basically a very flexible and open source tool, and it is designed to streamline creation of LLM applications. So it is like not just RAG, many applications. It is basically an abstraction, and so it provides high-level abstraction, kind of like a wrapper for composing multiple steps in the process, which we refer to here as chains. So chains are basically the steps in a certain workflow, such as the retrieval step, the augmentation step, the generation step. So it has the chains, and LangChain also provides agents that can autonomously choose the right steps based on user input and memory features to improve the contextual relevance and responses over time. And LangChain basically acts kind of like the glue that ties together the different components of the RAG system. And like I mentioned, it is not just used for RAG, it is used for many other use cases. And I suggest that you also, take a look at the other things that LangChain does. And it also supports various integrations with popular LLM providers like OpenAI, Cohere, Mistral AI, and so on. So it provides integrations with many other LLMs. So next is Langsmith. And we won't really dive deep into Langsmith. It will just be something like a quick look. So Langsmith is basically a tool that complements LangChain by providing powerful tracing features. So what it does, it allows us to track the flow of the data through the RAG system and visualizes how the model takes decisions at each step. So this would help us debug and optimize how efficient our RAG system is. And with Langsmith, we can not only build, but also improve workflows because as we move on, we would identify issues and identify potential problems that could arise. So next, let's dive into the code. Now that we've covered the theory behind the RAG system, we had an overview of how it works. It is time to see how all these concepts come together in the code. We'll walk through how to load and process the documents. So how to create embeddings and store them in Pinecone. And basically we would have like a PDF and see how we process the PDF and how we prepare it to be able to store it in Pinecone, and then to create embeddings based on the processing that we did to the PDF. We create embeddings and convert it into convert the text chunks of the PDF into vector representations, and then we would store it in Pinecone. So we would insert this embeddings into Pinecone vector database. And lastly, building the RAG workflow where we will see it all come together. We will combine the retrieval, the augmentation, and generation using LangChain and LangSmith. So let me open the code. Oh, I just realized someone said the poll isn't showing. I didn't click on start the poll, so I guess that's why. So I uploaded it. And I see some questions. Okay, so someone is asking, let's answer these questions. Someone is asking, does the vector database include both the LLM and external source? So the vector database, it includes basically the context that you want the LLM to look at. So the LLM is a separate entity. It's something separate from the vector database. The data that the LLM has been pre-trained on is something completely different. It's separate. And what the vector database includes basically is relevant data that you want the LLM to look at. Like, for example, if I'm a professor that wants to create a chatbot for students, what I would put inside that database, what I would put inside the vector database is basically the course content. So this is what the LLM would use to look up. So when a student asks something, it would go and look up at the course content. So this is what we store in the vector database, basically. So Muhammad Rashad asked, how can we ensure the generated responses from a RAG system are not only relevant, but also crowded in the retrieved context and avoid hallucinations or inaccuracies? What evaluation metrics are important here? We'll go actually at the like after the coding part. I will cover that part. So I will answer your question after the coding. Yara is asking, how can the RAG pipeline be designed in a chatbot to retrieve data based on semantic, not only similarity search, to actually understand the user prompt? So could you clarify what you mean? So do you mean that so by semantic here, basically, let me know if I didn't understand your question well, but basically the RAG pipeline, when we give it the data, when we give it the user input, this user input is transformed into a vector. So this is transformed into a vector using a certain embedding model. And this is where it will be stored into, this is where it will be compared to the stored vectors in the database, basically. So this is basically like a semantic search. So the vector database, it transforms the user query into a certain vector based on the words that have been said. And when we do the similarity search to the vector database, we can see that the most similar words or the most similar phrases would be closer to that. So it would be closer to that certain query that the user gave. One of the disadvantages of LLMs is that they become outdated. Doesn't a vector database have the same problem? Not really, because you have control over the vector database. So you are controlling what's coming inside the vector database, what's going outside it. So you're the one that's updating it. This is given that you're giving the LLM a vector database that you have control over, and the LLM is using the vector database as its content that it's going to look at. So it doesn't have the problem if you update it. So you would need to update the vector database, basically. Okay, let me share my screen for the code part. Okay, I've shared the window. Let me just connect it. So what will we be doing here in this tutorial? So we have, let's say, the use case here is, for example, a professor wants the students to be able to ask questions about their course. The professor doesn't have time to answer all the questions all the time. He's not available 24/7. So what the professor wants to do is build kind of like a small chatbot or a rack system that is able to understand the context, understand the lecture, or understand the course, and be able to answer the students based on their questions. Because if the student, let's say, uses ChatGPT, normally the ChatGPT doesn't have access to the lecture slides of the professor. So maybe the professor has certain examples that he wants to talk about, or has certain information, some certain specialized information. So this is where we want to use RAG, basically. So I'll give you an example of a lecture. So we will use this PDF. This is actually a real lecture that I used to. This is a real course that I used to take back in university. So it's a reinforcement learning course, and we will pass this lecture, the first lecture of the course, to the model, and this is where we'll build the rack system with. So before that, we need to have some. We need to initialize some things, and we need to have some API keys, and we will be using here as an LLM. We will be using Cohere. So this is all wrapped under LangChain. So as you can see here, LangChain chat models, and it has initialized chat model, and you pass on the Cohere model provider. And this is basically, you're able to get all these API keys. They are free to use. The trial versions are free to use. So we are using, for the LLM, we're using Cohere. So you would just have to log here into Cohere and get the API key. And for the embeddings, we will be using Mistral, and same thing for Mistral as well. Mistral has also a free trial, or like a free tier that you can use. So, and I will send you the links as well, and also the link to that notebook. So Mistral also, you would have to log into Mistral and get the API key to use. And next, the vector store. We will use a vector store called Pinecone, which is what we've talked about. And also here, I'm gonna walk you through how to, use Pinecone, how to upload on Pinecone. So we'll be using Pinecone as a vector store. And lastly, we will be using Langsmith. So same for Langsmith, you also need to log into it to get the API key. And basically what I did here is I stored the API keys here. So as you can see, the API keys appear here, and you can pass it on to the environment variables. So we've initialized the API keys, and we've initialized the models. Next, what we want to do is upload the PDF to Pinecone. However, we can't just upload it. There are some certain steps that we need to follow before uploading the PDF. And what we need to do first is pre-process the text. And so pre-process the PDF, turn it into text, basically. So let me upload the PDF over here. Here we define the pre-process text function, and it basically cleans the input by replacing consecutive spaces, new lines, and tabs with a single space to ensure that we work with clean and normalized text. However, obviously, there are more advanced pre-processing that you can do, and that is advisable to do because PDFs are usually not formatted very well. They can have lots of weird formatting. So this is just a simple pre-processing. And next we have the process PDF, and basically this loads and processes the PDF, and it splits it into smaller chunks. So it basically takes the PDF, splits it into chunks. So we define here the chunk size as 1,000. So this is the size of text chunks, so 1,000 characters per chunk. And we have a chunk overlap. And this chunk overlap basically means, so let's say we have 1,000 words. We start from 0 to 1,000, and then we have 1,000 to 2,000. But sometimes we don't want to, separate them completely. We want them to overlap, because what if you cut off, for example, if we are explaining what is reinforcement learning and the chunk cut off here, that means the next chunk is going to be different. It's not going to be connected to here. It's going to start, it's the same concept, and it's going to start from something, and it's going to start as a different chunk. So we have something called chunk overlap, and this is basically you overlap the overlap between the chunks. So let's say it starts at the beginning and ends here. So instead of the next one starting from here, the next one could start from here. And then it splits the documents, and then we apply the pre-processing here to the text that we get. And lastly, we create the embeddings, and this is using the the embedding model that we have defined over here using the Mistral AI embeddings. And the embeddings here, remember, is what transforms the text so that now you have the chunks of text. So you have like lists of chunks of text, and it transforms each list of this into a vector. So next we have the file path, the PDF. We give it the file path, we process it, and we do the embeddings and get the chunks. And to be able to observe the embeddings to Pinecone, let me first walk you in how to use Pinecone. So let me log in. So this is what Pinecone looks like. You basically go to database, and we have something called indexes. And basically this is where we would store the, like this is the database here, this is the project, and then we have the database. And we have index, which is basically, it divides the, if you want to store different things, you can divide from here. So I created something called React tutorial. But to create an index, what you can do is click create an index, write an index name, and then you can either you have different configurations to use. So you have different embedding models that you can use. So you can use the Llama from NVIDIA, you can use the Microsoft, you can use the Pinecone hosted one, or you can click on custom settings. But there's something that you should be wary of. So what you should be wary of is the dimension of the vector. So this depends on the dimension of the embedding here that you picked. So the embedding model that you've picked, what is the dimensions of the vector, of the output of that embedding model. So you can either pick that, or you can click on custom settings, and here you can define the dimensions. So if it's going to be 1024, and the metric to use. So is it going to use cosine similarity, the dot product, or Euclidean distance? And we have serverless, and serverless is the free tier that you can use. And the cloud provider would be AWS. I think the others are, you can use AWS. And then you would click on create index to create an index, basically. And let's see, we created, and we have this now. So let's say we created a new index, and this index, you can see that it has dimensions of 1024. So that means that the embedding models we use, like this is a customized one that I did. So I put the dimension as 1024. So this is the dimensions of the vectors. And after we do that, it is now ready for us to, upload the content to it. So what we need to do is copy the host link here. And then we have initialized it here. This is where you put it. And you also can, so here is where we upsert the functions to Pinecone. So we use something called upsert. So it upserts each basically vector to Pinecone. And what I did here is basically we have an ID. So when you upload something to Pinecone, it needs to have a unique ID. So this is data that I've uploaded before, so for you to take a look at it. So this is a unique ID. So to do the unique ID, what I did was create a random number and underscore the course name underscore the lecture. So lecture 1. So if we do lecture 2, it's going to be RL underscore lecture 2 and so on. So this is the unique ID. The values, you pass in the values, which is the embedding that we got from the previous function. And then the course name, this is metadata, which is actually very important to use because once you have uploaded your things here, you don't have any information on it. You literally just have, so let's say we didn't upload the metadata. Okay, so metadata here is course name, ID, lecture number, module name, and text, and the text that you did, and the text that you uploaded. So without it, it would literally just be the ID, and it would be a vector embedding. So it will be just a vector of numbers, and you won't be able to trace back where is this coming from. You won't be able to trace back where is this information coming from. Is it coming from lecture 1? Is it coming from which module? So it is super important to be able to trace back where is the information coming from, to put some metadata. And also, what I did was put the text because you're not able to see the text. So when you upload something to Pinecone, you can't see the text, like I mentioned. It's just the ID and the values. So what if you want to see what is the text? So we upload the text as well, and then it just loops over the chunks that we created, and it uploads it. So here is where it basically uploads it, and I uploaded in a namespace called tutorial. So this is the namespaces. Basically, it lets you partition an index into groups. So you can, in the same index, so in the same thing, you can have a different namespace. So maybe tutorial 1, tutorial 2, and so on. So this is basically after we've uploaded it. So next, let's try something. Let's try querying the vector storage. So we can ask it, who are the course instructors? Okay, this ran. It should be able to tell. So the instructors are Dr. Ahmed Sami and Dr. Yed Imari. So we would run this. This, what it does here is it creates embeddings for that question. So let me show you what it would look like. This is what an embedding looks like. It is basically just a vector or a list of numbers that we wouldn't understand, but the computer does understand. And to be able to query this, so what we want to do now is we want to find out who the instructors are. And this is not an LLM, so this is just, it looks up the instructor, it looks up the keyword, or it looks up this whole thing, and it gave it, like you've seen, it gave it like a vector space. It gave it like a vector. So what it does, it compares this vector to the other vectors here. What is it closest to? So, and it uses here cosine similarity, the metric that it uses. So let's try running this. And here, basically, what we're doing is getting the top 3 results, and we want to include the metadata because we want to see what is it getting. So the returned response. So the first, or the closest response that we got is here. We got the course ID, the course name, lecture number, module name, and the text. So this is the course name. This is this text is actually the chunked text, and that was turned into a vector. But now we have it stored as a text. So it was able to extract, as you can see from out of all these slides, it was able to extract where who the instructors are. And you can see here that is like it's getting some things that are not very that are not the course instructors. This is because we give it the whole question. We didn't just give it instructors, we gave it the course instructors. So it used course as also a part of something that would search for. So course would be close to lecture, no? So this is why it got this. And same from here. All right, so now that we have built the vector storage, let's start building the RAG application. So what we're gonna do first is we're gonna build the RAG workflow using LangChain. So we define here this is from LangGraph to be able to plot basically the how the process is going. So I'm gonna once we run this, you'll be able to see how it looks like. So we have here the retrieve function, and basically what it does, it performs a similarity search on Pinecone, and it returns the top 5 closest documents, so the top 5 closest chunks of text. And this is basically along with their metadata as well, so it gets the metadata as well. So this allows the system to get meaningful context for each one. Next, we have the query or respond. So this is basically, it generates a message because we don't always want to use the Pinecone. We don't want to always search for Pinecone. So this is basically a tool, or this is basically a function that you either give it query or respond. It passes in basically query or respond. So if it passes in, if the message state, for example, is query, so that means it's gonna go and query the Pinecone. If it's respond, it's gonna respond. So what it does is it checks if we need to respond directly based on the user's query or not. And then we have generate. So basically, once the documents are retrieved, the function takes the documents, content, and formats it into a prompt. So this is the prompt that we have. So we get the message, and this is the system prompt. So this is the prompt that you design, and this is where you need to do prompt engineering, and it's you need to do it well so that it wouldn't give you irrelevant answers, or it wouldn't go outside of what you're asking it. So the system prompt here, I basically told it you're a teacher, 2 students called Wally for question answering tasks. Where appropriate and relevant, help the students to think without giving them the answer right away. So when you ask it something, it would not always give you the answer right away. It would help you think it through. And use the following pieces of information of retrieved context to answer the question. So if the answer is not in the pieces of retrieved content, you must always say that you don't know. And use 3-sentence maximum, and keep the answer concise, be friendly and humorous, and say the answer right away. So this is basically the prompt, and then you pass in the documents that you got. So this is basically the augmentation part. So this, then after that, it passes it to the LLM to do the generation. So let's run these. So this is what LangGraph could help. It would help you basically visualize it. So now that we have like the defined essential functions for retrieval and generation, we would move on to LangGraph, and this allows workflows using nodes and edges. So here we have the query or respond function. We add it as a node. And then we have the tools function, we added as a node. We have the generate function, we added as a node. And set entry point. So this is meaning the first function that will be executed when the query is received. So is it gonna query the Pinecone database, or is it gonna respond? And then basically we define the conditions that control the workflow of the flow of the graph and links the nodes with each other. For example, if the query or response is triggered, it leads to generate. Yeah, we already ran it. Let me rerun it. So this is basically what it looks like. So we start, it goes to query or response. So then it either goes to tools and then generates. So here that means it would query the database and then generate, or it's gonna respond. So this is what a visualized version of it looks like. And here, what we want to do is actually try to have a conversation with it. So to ensure that the system maintains context across multiple queries, we use something called memory saver to store and retrieve the state during execution. So that means once you run it once, you can run it again and it will have the context of that previous run instead of, each time being independent. So this is useful for more interactive and coherent conversations, and it basically allows the system to remember the previous context of the prior interactions that we had. And basically, we define a configuration for the thread, and this basically assigns the thread ID to ensure that the conversation is, remembered throughout. So let's try running it. Here, basically, it's going to be a loop where you would type in a message and then the LLM would respond. So let's start by saying hello. Hey there, how can I help you? Let's ask it the question that we asked before. Who are the course instructors? So you might have noticed something different here. So it says here, I will search for the course instructors and relay information I find to the user. So this basically, this is kind of like a print to show that what keywords it is extracted from here. So it didn't look up Pinecone. It didn't look up the whole thing in Pinecone. It just looked up course instructors. So this is something that is also built into to the functions that we did in LangChain. So now that I gave an answer, it gave an answer that your teachers for this course are Dr. Ahmed Thani and Dr. Imari, and they're experts who will guide you throughout the world of reinforcement learning. So it is able to tell what course it is as well. So let's try asking it a different question, maybe a more difficult one. Okay, we can ask it, for example, what is tic-tac-toe? And if you've noticed, like tic-tac-toe, if you ask ChatGPT what is tic-tac-toe, it's going to tell you that it's the game. However, here, if we ask it, it should not give you a generalized answer. It's because it's here in this context is different. Give you an answer. So that means that the function that query or respond, it sometimes incorrectly said respond because it was generic. So what is tic-tac-toe representation? This would be also like one of the improvement points in the RAG system, so that it can be sure when to look at the data, when to look at the database, and when to not look at the database. Because if you ask it also like something generic here, it could assume that it's generic. So it's here it looked at tic-tac-toe representation, extracted these keywords, and it tells you it's a way to represent the game of tic-tac-toe using table of numbers. Each number represents a state, which is a possible board configuration, and basically more reinforcement learning stuff. So it's able to tell basically the content here. Does anyone have any questions they want to ask it? So no one wants to ask it a question. I mean, it makes sense because this is a reinforcement learning course. But yeah, so basically this is the rack system and how it how you can build it easily and using LangChain. So as you can see, it was relatively easy to build. It didn't take a lot of time. So you didn't train any models, you didn't train anything. All you had to do was just get the blocks and put them together, and you put them together also with the help of LangChain. So does anyone have any questions regarding the code or anything they want to ask regarding the code here? I will share with you the link of the code. So no worries, I'll share it. Yes, I'll share it here. So this is the link of the collab notebook. All right, so if there's no more questions about the code, let's move on to the next part, which is the next part of the presentation, basically. So let me share my screen again. Okay. So let's move on to the next part. The challenges in RAG and the challenges in lag, and the challenges we face in its implementation. So firstly, the quality of external data. It is very, very critical. And if the data retrieved is inaccurate, the model response will be too. So that means the data that you put in the put in the vector database, it needs to be accurate. It needs to be good. It needs to be good quality data, because if you give it bad quality data, that means the RAG is going to perform badly as well. Additionally, sometimes RAG system can face latency issues. So, because it has components such as retrieval and generation steps, so it could add to the processing time, and also handling ambiguity. So in retrieved content is another issue. So for example, imagine that you ask it a certain question and it found multiple answers to that question, to that same question in the database. And the questions, the answers to that question in the database, they're different from each other. So that means you're going to give the LLM conflicting information, right? So how do we handle ambiguity? And also, if you ask it like a question that isn't very clear, and it's not sure which context, which document to pick, so this could be also an issue. And maintaining up-to-date external sources is a challenge. And so the data that you have basically in the database, it needs to remain accurate and relevant. And there's also an issue that comes with having multiple sources. You can have multiple vector database that you want to look at. So it could be difficult to manage multiple sources. And also knowing where the data comes from. So for example, the reason why we did the metadata, as I mentioned in Pinecone, is to help us with the issue that comes from knowing where this data also comes from, like where does this lecture or where does this information coming from. And lastly, by using external databases, the RAG system can expose or retrieve sensitive information. So imagine you're a company and you have a database that you've passed, that you've, want to implement RAG with. The issue here is that you don't have anything protecting you from exposing sensitive information. So, for example, if a user asks something like, "What is the secret recipe?" and this is inside your RAG system, the LLM is going to answer. So it doesn't know that it's not. It doesn't know that it's private. So there are some privacy concerns that you need to do. Basically, you need to take care of. So for the data quality and accuracy, you should always make sure that you've use trusted and domain-specific sources. You need to make sure the sources are good. You need to pre-process the data that you're giving to the model. So the pre-processing that we did to the PDF, it was a basic pre-processing. But imagine, for example, if there's a huge PDF and there are some duplicate slides. This could be an issue, because that means these duplicate slides are going to be treated as different content. And when you ask the LLM something, it's going to get these duplicated slides and it might ignore other things. So you need to make sure that you pre-process the information that you're putting inside the database well, and you need to make sure that it is up to date and relevant and of good quality. And for latency, you can basically, one of the things you can do is parallel processing, the retrieval techniques. You can use parallel processing to make it faster, to make the generation workflow faster. And let's go next. So the complexity of managing sources is what we've discussed, kind of like you select basically you can add, have metadata. So to be able to pick which source to go with, you can make use of that metadata. And lastly, the privacy and leakage. What you can do is you can, before you give the LLM anything, so you can add like a privacy wall kind of. So before you give the pass-in to the LLM the content that could be private, it should go through some certain guardrails. And this is where, we have the guardrails in RAG systems, and this is something to make RAG more trustworthy in production. So guardrails are very essential. So we have kind of like pre-guardrails and post-guardrails. So the input guardrails, for example, let's say the user asked something irrelevant, or the user asked something inappropriate or unsafe. Before you even pass it, or before you even go to the Pinecone database, you can detect this irrelevant or irrelevant material or irrelevant question before passing it, before searching the Pinecone. So this would save you time. So what you can do, kind of maybe use as an example, like a one-shot model that would, if you want to detect something that's toxic, you pass on the phrase and it will detect if it's toxic or not. Especially in educational areas, the student shouldn't ask stuff that's toxic or unsafe. So it would filter that before even passing it to the model, and you can do like a fallback response that would tell the student something like, I cannot answer that, or something like that. And you can also restrict the LLM. You can restrict it to what it's allowed to say using the system prompts. So you can like do prompt engineering to limit it to respond only from retrieved content. And you can also do the post filtering, so the guardrails that happen after the LLM gives the answer. And what you can do is also add some sort of guardrail after the LLM gives the answer to detect if this is irrelevant context, or if this is something that the LLM is giving you irrelevant context or not. And next, we want the LLM to say, I don't know. So if you ask it something, we need to say, I don't know. So you should add fallback responses when nothing relevant is retrieved. So if a student asked about something and there's nothing relevant that is retrieved, you should enforce a strong I don't know policy so that it doesn't hallucinate, it doesn't give you random stuff. But it depends also on the use case. You can make it more flexible. You can make it like, for example, if there's a course about music and a certain musician is not mentioned in the course, but the student asked about him, you can either make it more strict or less strict if you want the LLM to answer that, or if you want it to answer it from its own knowledge. Because that means if it didn't retrieve any content, it didn't retrieve any context, that means that it's going to answer based on its pre-trained knowledge. And lastly, the data privacy measures, which is the data privacy and leakage that we discussed in the previous slide, that you need to be careful of the data inside your data inside your vector database. And there is actually something called Guardrails AI, and this is basically kind of like a framework that applies guardrails to your RAG system. It's kind of like a wrapper that applies guardrails to your RAG system. So this is something that you can take a look at. And yeah, that's all. Thank you for listening, and let me know if you have any questions. I'll be happy to answer. Let me check the chat. Okay, so someone asked, for data scientists and developers looking to get started with RAG, what are some recommended tools, libraries, and best practices that they should be aware of? So I suggest maybe you could start with LangChain to get an idea of how the components work together before working separately on each component. So you can try out LangChain, play around with it to try to understand in depth how the components work. And also, I recommend understanding each component very well, because each component is pretty much kind of independent. So, and at the same time, they all, help each other out. So if one component doesn't do well, that means it's going to affect the rest of the components. So we need to understand the components very well to be able to detect if there is an issue with a certain component that would affect the rest of the the workflow. So, and yeah, the libraries would be try out LangChain and LangGraph, and the best practices would be like we mentioned, the number one thing you should take care of is how you store the data, and because basically this is what RAG is built on, the data that's inside your vector storage. So the best practice is make sure that the data inside your vector storage is accurate and it is clean. It is easy for the RAG to extract the the information coming from it. So this is very important. And also, once you get a hold of the RAG workflow, you should start trying implementing the guardrails, because in production, guardrails are super important. Like RAG in itself, it works, but it could have some issues like we mentioned. So guardrails are super important, because you can't risk, putting a RAG workflow and in production, and that is not good. So Abdurrahman is asking, what do you think about AGI? What do you think about AGI? I mean, like, in terms of how close we are to it, or like how far we are from it, I feel like AGI is still very far. The bots, the LLMs and the AI that we have right now, they're smart, but they're not as smart as humans. They're not as close as to the human brain. The human brain is incredibly insane, and like, for example, if you teach a baby something, it learns it much faster than what an LLM would, right? So the LLM is trained on trillions and trillions of data, but it still doesn't have that grasp. It doesn't really understand what it's doing. It's all basically numbers. So like highly intelligent AI, it's still very far, in my opinion, it's still very far from us. Like, I don't think it's gonna surpass, honestly, I don't think it's gonna surpass the humans. Maybe in some areas, like in automation, but in terms of like, intellectual thinking and how we think, how we solve problems, no, I think it's pretty far from, how the human thinks. So does anyone have any other questions? I think I missed a question by Abdel Fattah Guma. You're asking if RAG models are similar to the deep learning models of OpenAI and DeepSeek, like R1 and O1. Um, so RAG is pretty different. Like the concept of RAG is very different than the deep learning models, the R1 and O1, because RAG is not like the content that you give it to the like the content for coming from the database that you give it to the LLM. It is not trained on it. It is basically like an addition to the information that it has, but it's not trained on it. So if you give it like if it extracts some certain context and you give it to the RAG LLM, it's not going to be trained on it. It just has it in its knowledge, but if you reset the memory, it's going to forget it. So it's not trained on this data. All right, so I think that's all, and I hope you enjoyed the session. I hope it was helpful. If you have any questions, please reach out to me by email or by LinkedIn. Feel free to reach out to me. And yes, I hope you enjoyed the session.
Ending the day with such a clear vision of smarter, more responsible AI. That's all for Stream 2. Thanks for being with us at DSC MENA 2025. If you are attending the in person day in Egypt, we will see you there. Thank you.